So this is the third video in this series where I'm really just learning about the 65265. In the first video, I walked through a schematic and a PCB that I have ordered along with the parts, and just working really to build my own single board computer with this microcontroller. And the first PCB is pretty basic. It's really very similar to this SXB that you see on the screen. But then in the future, I'll iterate and add functionality to that and kind of learn as I learn more about this, kind of decide what I want to do with that board design. In the last video, I went and added an LCD, a 2-line, a 1602 type of LCD, and controlled that from the microcontroller, and that all went fine. This week, I've been working on interrupts. Having the LCD is a great first step. Second thing that I want to have running is a PS2 keyboard connected to this so that I can interface with it directly and not have to go through USB serial. As I was doing that, I was finding that interrupts were not working as I would expect them to work. And I'll talk through some of the stuff that I went through this week in this video. Ultimately, I did get it working in one configuration. There's another configuration I'd like to eventually get it to work in that I could not get it to work in this week. And maybe would ask anybody that as I get to that, if you have ideas or you have code where you've done that before, if you could share, that would be wonderful. As part of the work that I did this week, I also switched to an external flash for my ROM, and I'll talk through the process of making that change. And I have that ROM, basically the code that I have on that, automatically loading when I reset the system. So basically I reset and it goes straight into my ROM. I don't have to mess around with uploading to RAM and jumping to RAM and things like that. And then in this video, I'm going to just simply use a button for my input to trigger an interrupt. At some point, I will switch that to a keyboard, and I'll talk more about that when we get into the actual walkthrough of what I have here for hardware. As far as resources I've been using, these are the resources really right here. There is a data sheet for the 65265 itself, so this is the microcontroller. That controller is on this SXB board, and there's a data sheet for the SXB board along with a schematic. On the 65265 microcontroller, there's also a monitor ROM. It's basically a ROM that's built into the chip that actually is what initializes everything when you turn it on, and that ROM runs basically this small monitoring type of operating system or code. So there is a reference manual for that. There is source code for that out in GitHub that Western Design Center has shared. And then within, of course, this microcontroller, the processor is the 65816. And there is a data sheet for that. If we get into interrupts on this microcontroller, though, there are 29 what are called vectored interrupts. Basically, there's going to be an address, and there's two tables you see off to the right. If you just pick a table and look at it for a minute, maybe I can zoom into one of these, you'll see that there's a series of addresses. And with each address, they kind of say, what is this for? What specific interrupt is this address for? And there's a label for it and maybe a description or a better few words to describe it, I guess. Well, really what's here is just simply places to store 2 bytes of data to point to an address that you would jump to. So at FFA0, there is going to store an address to jump to if there is this UART0 receiver interrupt, if that gets raised or triggered. If timer 7 goes off, it's going to go out to FF8E and F and then read the address there and jump to that. That's the idea with these tables or vector tables. So down here, I mentioned there's a few different types of vector tables depending on which mode your microprocessor is in. There's a native and an emulation mode, and that's going to make a difference on which of these tables gets used. Also, there's something called shadow vector tables, and I'll talk more about that later. But when it comes to all of these different interrupts, some of them are software created. So in code, we can say do a break, and that might trigger an interrupt. There are some hardware interrupts like an IRQB, which is really just a level type of interrupt. So anytime, let's say, I take this line IRQB and I pull it down to 0 volts, it's going to just constantly trigger that interrupt until it's brought back up to 5 volt. There's timers, and when the timer hits its time, basically it fires off an interrupt. There's edge triggered GPIOs. So I want to take a GPIO pin and either have it when the edge falls, so I go from a 5 volt to a 0 volt, that triggers it, or vice versa, a rising edge on the edge. So if it goes from 0 to 5. And there are different pins, and I'll show that coming up. But not every pin can have an edge-triggered interrupt, and the ones that can, they're going to support either a rising or a falling, a positive or a negative type of an edge. UARTs have interrupts around transmit and receive, and then there's also a parallel interface bus, or PIB. What I'm going to work with in this video is edge triggered, because I want a PS2 keyboard, and on the PS2 keyboard there's really only 2 wires coming out of it. There, besides power and ground, there's going to be a clock signal and a data signal. I want to use that clock signal to basically cause an interrupt to run, and then I can go read the data that is associated with it. And that interrupt, basically, I want to happen when this clock edge falls. So when it goes from 5 volts down to 0 volt, that edge is when I want to run my interrupt to then check the data on the data line at that point. So that's what we're going to work with in this video, where I'm going to kind of walk through what I've done to get that running. Now, to make all of this work, there are going to be a whole series of registers that we'll have to work with. So there are control and status registers, and I'll zoom into that here on another slide. You can see some of them here real quick on this slide. I just copied this out of the data sheet. These are all from the Western Design Center data sheets. And there's also a global inhibit bit. So on the microprocessor, there's essentially a flag that says don't allow interrupts. It's an inhibit bit. You have to clear that. Clear the inhibit before interrupts will work, and that's done pretty simply through code with a simple CLI command or operation. Looking at these edge interrupts, because again, that's the type I'm looking for. I knew going into this I wanted a falling edge interrupt. So I looked at the table off to the right, and that talks about some of these registers that I can use to control setting up interrupts on different pins. Off here to the left, these are the pins that are edge interrupt capable, and you can see there's some that are positive edge, some that are negative edge. So I was looking at the negative edge. There's 3 of them, and it ends up on the SXB board. 2 of those are used for the UART that you primarily communicate through the USB connector on. So that kind of ruled those out and really took me down to just P64. So for the rest of this video, that's what I'm going to focus on is P64. So it's port 6, pin number 4, which is like the 5th pin. So it starts at 0. So 0 through 4, the 5th pin is 4. So P64, we're just referring to port 6 and that pin ID 4. And that is a negative ID or a negative edge pin, so I can put an interrupt on it. So if it falls on that clock signal, I can run an interrupt. Now there are 2 registers right away that we're going to have to pay attention to. There's an EIER and an EIFR. And so EIER is an edge interrupt enable register, and here is more detail on that just down below. But this is where I can choose which of those pins do I want to set an interrupt on. So again, I'm going to be working with this pin 64. So there's an IRQ, an interrupt. They call it a NE64E, or it's a negative edge. Now in this case, I'm going to want to make sure that I can go out to this specific EIER, and that is at address DF45, and I want to make sure that I set this specific bit of that 8-bit register to a 1. And if I do that, that is part of the setup to get interrupts running. So that's saying which pin or pins are going to support interrupts. Later, after an interrupt occurs, I can go and read this specific register at DF47, which is an EIFR. It's an edge interrupt flag register. And I can read this specific bit, and if it's set to 1, it tells me that an interrupt has occurred. If it's a 0, it tells me an interrupt currently has not occurred that I haven't previously processed and cleared. So I'm going to have to work with these 2 registers, and these are the details of those registers, and you'll start to see that in the sample code when I get into that. Now my hardware setup, again, while I'm waiting for my PCBs, I'm working with this board, and one of the things I had to do this week is add an external flash ROM in the upper right. You can see that there's a socket here, a PLCC, a type of socket for a flash. And what I was running into, I was trying to, similar to my last video, assemble and link and create a hex file. And then through this EasyXXSXB software, upload that code essentially. And then from the monitor, which is again this little set of code that's running off of the built-in ROM, jump over to my code in RAM, and that worked great for the 2-line LCD I was working with. But when I get to interrupts, there's some problems with that, and I'll talk a little bit more about that. But long story short, to get interrupts to work, I had to set up my vectors where to point to, and that I ended up having to put onto a flash in this external flash that you see in the upper right in that socket. And within that, then I've put in code and identified my vectors so that when one of these interrupts occurs, it can know where to jump to process my interrupt. I was trying to do something else around this shadow vectors, and more to come on that here in a little bit. Something else I did then is I connected a push button to P64, basically down to ground. So if I push the button, it takes that pin and puts it down to ground. So P64 would be in this port 6 over here, and then it'd be pin ID 4. And the way this works is, let's see if I can maybe turn to a little laser pointer here. Down here on this connector, pin 1, and these are, you can't see it on this board, but there's a tiny little dot off by this pin that tells you that it's pin 1. It's the first pin in this set of 10. First pin, if I recall correctly, is going to be power, and then there's a ground. And then I would get into P6, 0, P6, 1, 2, 3, 4, 5, 6, 7. So 0 through 7, that's my 8 pins within that port. And all 3 of these kind of follow that pattern. So P5 would be power, ground, P50, P51, P52, etc. So I'm working on P64. So 0, 1, 2, 3, 4. It'll be this pin right here that I am going to be working with. And I basically put a little push button on a breadboard along with not quite right RC circuit just to help with debouncing. And I'll use that here coming up. And when I press that button, what it's going to cause is this pin to go from a 5 volt, because I'm putting a pull up on it, to 5 volt. The button will cause it to go down to 0 volt. And that transition from high to low will cause an edge interrupt to occur. This memory map is pretty important to pay attention to. Maybe what I would point out, you can probably ignore these top 3 rows that are marked with chip selects 5, 6, and 7. I do not have this memory or this user memory up here, or the one above that. These are addresses I don't have access to because I don't have that hardware. But the actual chip itself, there's this CS2B it shows, and it shows all of this breakdown of addresses in here. And some of the important ones are going to be like this FF00 through FFFF. That is where the default interrupt vectors are. So this is in the chip itself, and it's basically programmed that if you hit certain types of interrupts to jump to a certain location within the monitor ROM. And if you want to change that behavior, then you've got to replace this internal ROM with external ROM, or do this shadow ROM. And again, I'm going to come back to that later. The board I have, this SXB board, has cache memory or static RAM on it, and it's going to use this address of actually 0000 through 7FFF. And that's also going to be important because I know that that's where I can write stuff to when the system's running. I also have to be careful because this monitor ROM always starts, so when I turn on the system, it's the first thing that fires up, and it does some so it runs through some routines, and either it comes up with the full monitor, or you can, somewhere in the middle of its startup, pass over to your external flash if you configure it to do that. But there's things it's doing and some memory that I suppose it's using, which I don't know in detail, but I just know you have to be somewhat careful there and understand how it's working. And then there's ROM memory. So I added that external ROM, and that's going to give me this 8000 through FFFF. So basically there's a 32K there. The ROM chip that you install is 128K, but you get you can configure it which of the 4 32K sections are active. Don't know if that's really banking or not, and maybe banking is the right word for that, but you can configure which of those 32K is active. Something else to point out in the cache memory, there's some upper 7,000 addresses that are used for shadowing. So off to the left, I just mentioned that the on-chip vectors are up in this F range, so FF00 and above, or maybe there's actually, yeah, they're all going to be up in there, I think. We can double check that as I go forward here. And then there's this cache memory, and that might have some vectors in it that are these shadow vectors. So more to come on that. When you take a look at the sample code that comes, there's only a few sample projects from Western Design Center for this board, which is a little surprising, and they seem pretty basic. But they do have a block in the sample code called shadow vectors. There's a vectors, and it has all of these that start at FFE0 and work their way up, or there's actually some stuff underneath that, I believe a little bit earlier than that, but they have a table that shows all those addresses. They also include this in the code, and they're pointing to 7E0. So remember, that's back in the basically this cache RAM, the static RAM that's on the board. My understanding of how this is supposed to work, and this could be wrong, and keep in mind I've not been able to get shadow interrupt vectors to work, so anything I say here you might want to disregard anyways, but what I believe is supposed to be the case is that for every one of these addresses you see up here in the ROM at like FFE0, E2, E4, E6, etc., there is an equivalent basically vector that you can write to at this range. So instead of starting at FFE0, you start at 7E0, and then you go to E2, E4, E6, and work your way up. And that'd be the interrupt vector for each of these things that you see here. Most of those probably you're not doing anything with, so you point it to this routine called badvec in their example, which really doesn't do anything. But one that maybe you do put an interrupt in for is IRQB, RK, or this FFFE. And then if that interrupt ever happens, it'll basically jump to, in your code, whatever you've labeled as IRQ handler. Well, you can't update the ROM in the chip, so you have to come to this address, and it'd be like 7EFE, and whatever you point to in those 2 bytes at FE and FF, you can point to a routine, and if that interrupt happens, there is some linking between the FFFE and the 7EFE. And if you update what's in memory at 7EFE, then you can point to something that it will supposed to be able to jump to. So the long version, and I'm sure I'm not explaining that well, though, it's allowing you in RAM to point to a routine that you want to run when that interrupt occurs, without having to replace the ROM, which you can't replace in the chip itself. So this I could not get to work, and what I had to do instead is just put my own external flash ROM, and then that gives me now control. I can actually tell it, don't use the internal ROM at all, use my external ROM, and in my external ROM I do have the ranges all the way up to FFFF, and I can, in the F range, put in all of my interrupt vectors. Something I found, and I'm still finding pretty frustrating with the shadow interrupt vectors, I can't find documentation. I've gone through the data sheets, and it really never talks about shadow anything. I think if you're going to figure this out, you probably have to go into the source code for the ROM monitor and see if you can reverse engineer it, essentially. There are no sample projects that I can find anywhere, whether from WDC or elsewhere, that show the use of interrupts, which I thought was interesting. I cannot find any examples that have interrupts working in them, and I cannot find anything that does anything with the shadow interrupt vectors. I could be missing stuff, but I've scoured and I cannot find anything. The closest I can find information is using AI, like Microsoft Copilot will come back and tell me all kinds of stuff about shadow vectors, but I really can't pin it down where it's getting the information from. I'm guessing some of it's from GitHub and maybe things that, I don't know, I can't find in GitHub directly. Anyways, documentation code samples seem to be lacking, and if anybody knows of documentation around shadow interrupt vectors, or especially important would be to go with that, or in addition to that would be any code samples. I'd love to see some code samples so that I can try to leverage shadow interrupt vectors at some point. So shadow interrupt vectors are off the table, and because they're off the table, that's where I went to the external flash, and I'm using interrupt vectors in the F1000 range, the upper Fs. Something else not to overlook if you get into interrupts, you're going to set up interrupts on certain pins, and I believe you're going to want those pins set up as inputs. So whether you're reading or writing on those pins, like a lot of, I guess, a lot of different types of I/O pins or GPIO, but you'll want to make sure that you set the direction as an input, not an output. And there's going to be a register for that. You can see off to the right, here's another listing of registers, and this is for basically different ports. So ports and other things, but I said I'm going to use port 6. So I can see with port 6, there is a thing called PDD6, and it is at address DF26. And then within that, I'll be able to say for this specific pin, I want it to be an input. So pin 4, pin ID 4, I'll have to make sure that the bit for that is set to a 0 so that it's treated as an input. So maybe here's some of the basic initialization and enabling. CPU mode is gonna matter here, and there's a couple things that are confusing as I get into this. There is an emulation and a native mode for the microcontroller, and there's an emulation and native mode for the actual microprocessor. Here I'm referring to the processor, so the CPU. It has a mode, and you'll see that when we get into this. I'm using a certain mode, and if I use a different mode, all of the vector addresses are different. So there's different tables depending on which mode you're in. You're going to want to initialize your stack pointer. If you're using GPIO, set the direction. You're going to want to set up your interrupt vector, so make sure that you're pointing to a valid ISR. Here is an interrupt service routine, I believe, ISR. So basically a routine that vector will point to. Then you'll have to make sure that you've enabled which pin should support interrupts. And again, I'm going to be using an edge pin, and I'm going to use this P64. And then you have to make sure that IRQs are enabled as a whole on the microprocessor. So here are some of the registers I'm going to work with. EIER, that lets me modify my edge interrupt enabling. EIFR will let me check which interrupts have occurred. PDD6 will let me modify the data direction for that pin that's going to pay attention for the edge for the interrupt. And then PD6 is just the data register for the port itself. And I guess in this video, I'm probably not going to use PD6, but once I get to reading the data off the PS2 keyboard, I'm going to have to use that PD6 to, assuming that it's one of the other port 6 pins that I'm going to use, which right now I have it plugged into, let's see, 0, 1, 2, so 2. So PD62 is what I'm going to use for my data, and PD64 is what I'm going to use for the clock. So when the clock triggers an interrupt, I want to then go read the data off of PD62. So I'm going to just jump into code walkthrough and just, I guess, maybe do my best to walk through this and try to describe what I have set up. I am by no means an assembly expert, so I'm sure you're going to see things in here that can be improved. And if you have suggestions, yeah, definitely please let me know, and I'll do my best to get things improved for the next iteration here. But I'm going to flip over, I guess in this last week, I did switch over. I had just started in Notepad++ for the last video for doing any coding. Now I'm kind of jumping into this editor here, and I'm sure a lot of you are using this, but Visual Studio Code is what I'm using here as we get into this. And you can see I've got a lot of files in a folder that I've been working on, and you can see my very advanced version control. I just periodically save a copy of the file is all I'm doing for now. I suppose at some point I'll get this stuff in GitHub, but it's not there yet. So let me go through this file. A lot of this is just standard stuff that is in basically the samples from Western Design Center. So I just grabbed one of the, like the LED one, and use some of the header formatting just for some consistency there. And then there's a whole section of these constants or equates, and you can see, for example, I'll point out a couple of them. PDD5, it points to this address. It says that that's the port 5 data direction register. PD5 is the actual data register. Here's some of those different control and status register maps. So there's some for UARTs. There's a pair of them for timers, although only one of them is defined. I think there is I could be wrong. Maybe there is I would expect a TIFR. I probably just don't have it set up in here. Oh, actually it's down here. So here's a TIFR. So, you know, you've got basically a place to enable, and then you have a place to understand, have the interrupts occurred, either for UARTs, timers, or in my case, I want to work with edge interrupts, like I mentioned before. Now, real quick caution here. The data sheet for the 265 has a lot of errors in it. A lot of typos, misinformation, information that contradicts other information in the same document. And here's one example for EIFR. On page 14 of the data sheet, it says, well, that's DF47. But if you go to page 24, it says it's DF45. And so they swapped a couple around, and I'm making the assumption that, and I had made the assumption that the bottom one was a typo on these pages 24 and 25 because all this other stuff pointed the other way. So page 14, the actual monitor ROM source code and any sample projects used it as you see here. So I just left that note in there. So be careful if you're looking at these pages, just ignore them. You'll notice that some of the captions in the tables are incorrect on these. You can tell that the tables were copied and pasted. And I'm surprised over the years this never got updated, which makes me wonder, are people not looking at the data sheet or just simply not using this or haven't used this microcontroller that much? I don't know. There are other registers maybe to get in and work with a UART. And at one point I went into UART2 because this pin I'm going to use is also tied to UART2 on the SXB board. And I disabled all the UART functionality on UART2. Later, the way I finally got it done, that was not necessary, but I left that definition in there. Then there's a bunch of equates for the pins. Again, I'm going to use this NE64, so I just have this to remind me that that is the pin. When I go to enable it in the register, it's that bit that I have to modify. And so I'll use this NE64 enable when I get to that. Oh, a bunch of timer and latch stuff I'm not doing anything with. A whole bunch of, this is a vector table if your processor is in emulation mode, and it just shows what addresses in the FF range are used for which different IRQs. And one that catches my attention right away is this one, IRNE64. It says that's the native or negative edge interrupt, and that would be if I am in emulation mode. And then it says it's at address FFD8, so I have to make sure that that is filled in, pointing to a routine that I want to run. And maybe I will jump way down to the bottom of the code where I have those and maybe work my way back up to the top here in a minute. So this is a block that is pretty much in the sample code. So when you open up one of the sample projects, you'll see something that looks pretty darn close to this. But this shows, all of these addresses. These are in the built-in ROM by default. And this just says that if I hit this IRQ BRK, I'm going to point to IRQ handler. So then I have a procedure up higher. If I scroll way up, IRQ handler, what do I want it to do when that interrupt occurs? And then there's also all these others that we're just saying bad vec. We shouldn't have those interrupts, or I'm not going to do anything with those interrupts. And it just goes to this bad vec handler, which really doesn't do anything in it, especially the sample one doesn't do much at all in it. So those are set up, but then I also came in here and I set up these. And so in this case, this is no longer correct. So I'm going to actually delete these lines because they do matter in my system now. But basically the way this is set up is, depending on which mode you're in, you have to know which address to set up this basically pointer. I set up these for all three addresses, and I don't think all three are necessary. Only one of those should be necessary. And if it ends up that I'm in emulation mode, I can go way back up here and see that negative edge P64 for the emulation mode vector table should be FFD8. And I think what that means is down here, I need this one. But these other two sections probably could get deleted, and I would be perfectly fine. I'd also previously tried doing some vector table work. This is a sample table they include in those projects that you can download. And they're pointing to a region 7EE0, and then these are all the interrupts, and these are just comments, of course, but this is just saying, okay, the first 2 bytes of this 7E, E0, and E1 are for this interrupt labeled like that, and it should jump to this when it occurs, and you can read through that. But if you go look up documentation for the shadow vectors, and a lot of this is coming from AI and places where I can't really find real good documentation, it's saying that you either have to be in this 7E90 or 7ED0, depending on if you're in native or emulation mode. And then these should be the addresses 7E98, 7ED8. So at one point I had these in here trying to get this to work, and again, failing to get that to work. But this would say, depending on which mode my processor is in, I have both entries just to be safe. go out and run this IRQ handler if that occurs. But again, I'm not using shadow RAM or the shadowing of these interrupt vectors because I could not ultimately get it to work. Okay, so if I go back up top, keep scrolling down, I think that pretty much gets me to where my code actually kicks off. I will jump down here to my org. In the sample programs, they're doing an org 2000. And if I go back to, I'm just going to step back here to the memory map right here. So 2000, I look through this and say, well, where's that at? Well, this is the 0000 to 7FFF. So basically, this is my cache memory. It's the static RAM that is external to the microcontroller. So the microcontroller in it has both RAM and ROM, very small amounts, but then the SXB board does include an external static RAM, and so that's going to be in this address range. So when I'm over here, org 2000 says, I expect this code to be, right in that static RAM within at 2000 within this 8000 range. But since I, from the last video to this video, switched to an external flash ROM, I'm actually going to expect my code to be at 8000. And if I look at 8000, that's the beginning of the ROM memory, the beginning of the external ROM memory. So that's why you're going to see this org has changed now. I also started out with the very first thing in that space at 8000 is these three characters, WDC. If you do that and you write this out to an external flash chip and put it in that socket, when the 65265 initializes and it's coming up, it will actually check that specific location on that chip, and if it finds it, then it kind of stops the rest of its processing and setting up of interrupts and all kinds of things like that, and it actually passes off or jumps to whatever is right after this. So it would jump to my SEI in this case. So that's what I did. I just said, okay, let's start at 8000. Let's write in those three characters, WDC, write that to the flash memory, put that flash memory chip into the socket, and then it boots and basically comes up right here, which is great. So then I've got some normal stack getting things set up, and I'm assuming the processor is in emulation mode at that point, and I believe that is correct based on everything else I'm seeing. So the monitor code starts early in its startup process. It kicks over to my external flash, and at that point the processor appears to be in emulation mode. Then I continue from there. I go out to all three of these registers that have to do with interrupts, and I disable everything because there could have been stuff that the monitor ROM set up for interrupts that I kind of want to turn off. I don't want it doing timers. I don't want it doing a watchdog. I don't want it doing anything. So if I set zeros in each of these registers, and again, you can look up these registers in the data sheet and it'll tell you which bits are for which different things, like which UART 0, 1, 2, 3, which timer, which edge pin, etc. But I'm just saying kill it all. So get rid of all of the interrupts, disable interrupts on all of the pins, because I don't want to use any of that interrupt stuff that would have been set up by the monitor. Then I go in, and not only did I disable them, I then clear. So this is the UIFR, TIFR, and EIFR. So I clear any pending interrupts. In other words, an interrupt happened, it hasn't been processed and cleared yet. I just clear all those flags, saying nope, just assume we don't have any active interrupts at this point. There's a parallel port interface. I disable that. Then I go into port 4 and I tell it that these two pins basically are for output. And let me actually just jump over and show you what I have sitting in front of me as far as my actual setup here. So this is the board that I'm working on. Here you can see I have an external flash in here. I've been using this header right here to control this LED, again, or LCD screen. You can go back to the last video if you want to see more on that. But then on this port over here, I have two pins. One is going to go to the PS2 data line, and you can see I have a PS2 keyboard plugged in, data line's coming in, so I'll be able to read that. And eventually then I'll also hook up the clock line to this orange wire, which I'm sure is hard to see in the video, but that'll be my interrupt line. Well, for today, that interrupt line is going to this button. And so if I press that button, I want it to do something instead of the clock signal coming from the keyboard. But what's in the code right now, this PDD4 is over here. And what I've done is I've taken the last two pins of that port and I'm kind of using them for debug purposes. So basically I'm going to generate a square wave. And so if I hit to certain spots, I'm going to flip it from a high to a low, low to a high, and just be able to monitor that on my oscilloscope to see, kind of use it just as a little debugging flag so that I can physically see if something is working the way I want it to. That's why you see right now I have my oscilloscope, one of the channels just hooked up to one pin, and then this other one is actually going out to an LED because I'm going to use that as an output with this test LED, and I want to be able to toggle that LED every time I press the button. Also, I want to be able to write a character to the LCD every time I push the button. So that's what you're starting to see here. I'm saying go to PD4, this port here, and I'm modifying the data direction, set the last two pins to be output. Then I go to PCS or PCS7. So port 7 is a special port, and it's used for basically enable pins. So there's different enable pins to enable the RAM, the ROM, or different things. PCS7 is tied to the CS2B. So if I go back up to the memory addressing, and somewhere in that table it says, okay, CS2B is the chip select for all of this to be enabled. And what they've done with the board, the SXB board, is they've also put an LED on that pin, which I thought was safe to use, but then I later found that that was not safe to use. So I was trying to toggle the LED, and other things were happening behind the scenes without me doing it directly that were causing weird things to happen. So I ended up kind of learning, don't mess with that LED. Find another pin, and that's why I connected my LED to a totally different pin that has nothing to do with the chip selects. Now, very likely there's something I'm not doing right there, but that was my experience, is that I was trying to modify that LED output. I was actually trying to read the status of it and write back out, and it does not work like a typical register. At least the way I was approaching it was not working. So, but this is if I want to use that LED. This is basically coming in and saying, okay, it's port 7, pin 2, so here's the flag for it. Go ahead and set that to a 1, meaning I want it to be output. And then I also have a little flag in memory just to remember what's the state of the LED. But later in the code, I don't use this PCS7 anymore. And instead, I'm going to use this one that I have connected down here. I made a little routine called P46 toggle. It just takes pin 6 on port 4 and toggles it. If it's high, go low. If it's low, go high. I have a routine to set up my LCD. I have a routine again here to toggle. It's the same routine. I'm going to toggle. I'm going to set my LCD. I'm going to toggle. So on my oscilloscope, I should be able to see this full go low to high to low, or vice versa, whichever way it was, and let me see that when this is starting up. And then I have a routine to set up all my interrupt stuff, and that's what I do want to kind of jump into and walk through the detail of that here. I'll look at each of those routines as I scroll down, but more to come there. At the end of all that, it's going to fall into the main, and in the main, I'm just going to basically loop. So basically at the end of main, jump back up to main. So this is just a constant loop. And every time I jump from this line back up to here, it's toggling this P46. So I'll be able to see that on my oscilloscope. I'll be able to see a square wave repeat basically here. Okay, LCD setup, I'm not going to go through any of that. So anything that says LCD setup, that's just setting up my LCD. If you're interested in that, go back to the last video, or I'll get this code posted if you want to take a look at it. But then I have this init interrupt. And so as a reminder, I'm using these pins here. PD64 for the clock, which right now today has a button on it instead of the clock line. And then PD62 will be my PS2 keyboard data line. Then I come down to PDD6, so that's the data direction, and I say that those two bits, the bit 2, so 0, 1, 2, 3, 4, those two bits are input, so I flag them as 0, store it back. So I read it, I AND it to basically turn those to zeros and then store it back. So that basically said those are going to be input lines. And then I come down here and I need to configure this EIER. And for simplicity, all I'm doing right now is saying, load up the bit that is the one that I want enabled and just store it into the register. Probably the more proper way is you load the register and then like do an ORA. So OR on the A register to basically flip the bit that you're looking to be enabled. But right now I don't have any other interrupts. I'm not worried about this. This code will work fine, but this above it is probably more proper. Then there's a thing called BCR, and this is, what is it, a bus control register. And this is another one of those that the documentation and everything I was maybe seeing through AI or other sources, it was really hard to decipher. But at the end of the day, there was a bit within this that I had to enable. One source said it was to make sure global interrupts were working. Another says, well, the datasheet says it's to turn on external ROM. Regardless, I have external ROM. It seemed like that made sense. But I was also finding documentation, not great documentation though, that was saying that if this isn't on, interrupts won't work on the microcontroller. So regardless, I have it on. So I load up this bus control register. I flip that flag if it wasn't already there as a 1 and store it back. I've got a whole section on setting up shadow vectors. I showed you earlier at the end of the code, you can set them in that way, or you can do it programmatically. So as this comes up and initializes, I can say, go out to 70ED8, and I want it to point to the first byte and the second byte of my IRQ handler, the address that's in there. So I've got one for emulation mode, one for native mode. I've got another one for emulation and native mode for a different interrupt, the plain old IRQB versus this negative edge 64. And there's also an IRQ break, and that has yet another address. So I was trying to get those filled in, again, with no luck, to get those shadow vectors to work. So that's all commented out for now. Quick routines on turning my LED on. This is the PD7, turning PD7, it's PD7-2 on or off. And then, as I mentioned, I was having problems with that. Not good to use PD7-2, and so I flipped it to use this port 4 and the very last bit. So this would be PD47 is how I'd refer to that. So 0 through 7, so PD47, and that's the one that I have over here on my breadboard. I have an LED right here with a resistor with a wire that goes over to that last pin, which is PD47. And so what that's going to do is just simply toggle or flip that bit. So I can call this and it'll toggle on and off that LED. And I have a routine that you saw get called earlier also, which is a P46 toggle. And that's the pin just right before the LED pin here on my board that my oscilloscope is hooked up to. And that's just so that I can, in the main loop, call this toggle and then see that square wave get generated. And as long as I'm seeing the square wave on my oscilloscope, I know that I'm in the main loop and the main loop is running, and that the microcontroller isn't locked up because of something wrong with my ROM code. Oh, then there's a whole bunch of functions on LCD stuff. I'm going to skip all of that. Here's my IRQ handler. So I'm basically pointing to this IRQ handler for that edge interrupt. So if the edge drops on that pin that I'm paying attention to, 6.4, I want it to come in here and toggle my LED, which is, again, not the onboard LED, it's the offboard LED I have. I want it to print a character to my LCD, a $ character, and then I want it to clear the flag for that interrupt. And this is how you clear a flag. So you basically say, well, in my case, I'm saying load up the bit that is the enable bit for this EIFR, so I can check if it was actually interrupted, so if there is an active interrupt. But to clear it, you write a 1 back to that EFIR, that same bit. So this basically is going to load up a 1 in the appropriate location and write it back to the register, which clears that interrupt. Now this code is not very good at this point. I should first be checking of, was the interrupt actually for that specific NE64, and if it was, then go ahead and clear it. And I'll do that cleanup later. I just haven't gotten that done yet. And I know for now, the only interrupt that should ever get here is this NE64. And then I'm back down to my vector tables. So that is my code. Now, if I show you how this is working, first of all, here's the board, and I've got my external ROM here. There's the external static RAM up here. I'm going to reset the board. And you're going to notice as soon as it resets, it reset my LCD, and that might be bright or not bright on the recording. But when I have it reset, I basically configure the LCD. I put the cursor at the first position. A couple other things I notice on this board as I look at it is, one, there's this CS2B LED that is on, because I do turn it on when the system initializes it. I do tell it to turn that on. I just can't read back the value of it. Something weird going on there. So I just said, fine, I'm not going to use that one. But I also see that this LED over here with my external flash is on. And that's because it's actively reading from that right now. And what would it be doing? Well, it's up in my main, I'm sure, because I've got a loop there. So it's just constantly here reading these couple of lines, basically the assembly off of that out of those locations. So it's just spinning through that. There is a little LED over by the static RAM. So if you see that light up at any point, that's when I might be reading or writing static RAM. But right now it's in ROM. It's working on this. That's my assumption, and I'm going to believe that's probably true. Now, something I will do is pull up my scope. This is just a little Windows app that shows what's on my scope right now. But you can see I'm getting, this is showing live update. I'm getting a 52 point something hertz square wave coming out of that system. And basically that's how fast it's coming out of my main loop. So does that sound right? I'm not sure. If I'm really running at 3.6 megahertz, should it really be that slow? Or maybe there's something with my clock that still isn't right. I don't know. But this is what it's generating right now. And, if I zoom into that, take a look at that. But basically, this is being generated from my main. The main is jumping down to this P46 toggle, and it's going through and doing this work here, which is basically load up what's currently going out of PD4, flip this bit, basically, so exclusive OR it, and then store it back. So that does give me some confidence that that main loop is running. If I go back to looking at my webcam then for a minute, so right now the screen is initialized, this LED is off. This little board, this is just a cheap little breadboard, but what I have hooked up to it is I've got my PS2 keyboard up here. The keyboard requires power, ground, and then it has the data line, the clock line. So that's essentially what I've connected up here. data line, clock line coming into the breadboard. The data line does run over to the SXP board, but I'm not using that yet. The clock line I'm not connected to. I'm not doing anything with that. Instead, I'm bringing this interrupt line over to this button. And so what should happen if I press the button, my LED lights up. And when it did that, I did notice, and I'll flip back to my oscilloscope, as I press a button, you'll notice that for a little bit it quit making that square wave, because that's because it got out of the main, went over and processed my interrupt, and that took some cycles where it couldn't be generating this clock from the main, or this wave that you see. So I'll press it again, and you might see it get, well, see, now we're not going to see it on here, and it might just be off the screen. Let's see, I'll zoom out a bit and see if we can notice it this way. So there you go. You see that gap there? That's when it was out processing my interrupt service routine. And so every time I press this, that quick gap is while it's doing something else other than cycling through the main. So looking back at the board now, then you can see this LED is on. Now if I press the button, LED is off. I press it again, LED is on. And every time I press, it's also over here writing a $sign on the screen. So you know, my next step will be, of course, read the actual data from the keyboard. So every clock, I believe there's 8 clocks to every keyboard key that you press. Every byte of data, basically there's a start, stop, and parity, I assume. And then there's 8 bits of data. So I'll take those 11 interrupts, I'll assemble that packet, and I'll have my byte of data, keyboard data. And I think some keyboard things generate multiple bytes, but I'll be able to pull out the keyboard data and then actually write out the real character here and not just a placeholder $sign. But that'll be next step, is for me to do the keyboard work. Now, anytime you're doing these interrupt service routines, you know, you want to get in and out of it quickly. And what I'm doing here of writing out to this LCD is probably not something I should be doing. Instead, what I should do is probably write it into a little, like a buffer, a little ring buffer of some sort. And then in the main procedure outside of the interrupt, have it, you know, clean out that buffer and write the characters to the screen. Just because you want to get out of an interrupt service routine as fast as you can. But for now, what I'm doing, this doesn't matter, but it's let me test this setup. So that all appears to be working. You know, I'm getting my square wave in the main, the button, when I press it, it's taking a line low. It's processing my code that is toggling this other bit on the output, and it's writing out a character to my screen. So that's all good. Now maybe I will point out one more thing on the external ROM. So this right here, I've got this external flash. It is 128K flash, which really the processor, or this 265, is only going to be able to read 32K of it the way this board is set up, and you can pick which of the 32K. I'll show you when I go out and I get done saving, you know, my code. I'll then flip over and want to build it. And I've just been doing that from a command line. So I have a window down here I can go to. And I'm just running this batch file that's in that folder. And it builds, basically assembles and links. And it shows me that I've got my code at 8,000. It shows me how long it is, or the size of it. Shows me I have some vector data, and it cuts off the name, it truncates it, but I have something at 9.8, B8, D8, and E0, and there's a bunch of stuff at E0. And you can see there's a bunch of things here. Now what I can actually show you is what's inside of that batch file. The one that comes with the sample programs is going to look like this, plus these bottom 2 lines that I commented out. This is basically going to do the assembling and then link it and have a few different types of output. I added this additional pair of lines. Actually, I don't even need the ones above it because I'm only using this one down here right now. This does the assembly, but then I output it in a raw binary. And I know one of these up here creates a bin file, but it's got a bunch of garbage, not garbage, but stuff before my actual code, and that will cause a problem. So this is what I'm doing to actually create the bin file. And when I create that bin file, what I'm looking for is when I open up my programmer for my Flash, and let's see, I think I do have that open here. What I want to make sure of is at the correct address, and I'll start by just going to 8,000. So I'm going to jump over to 8,000 in here. You see what the very first thing is? It's WDC. So that, and I don't think I can zoom in this program. It's hard to see, but it's WDC. It's the very first 3 bytes in here. And that, remember, that needs to be there if I want the monitor ROM to automatically jump to my external flash. So that has to be there. And so when I create that bin file, it has this at 8,000. There's no preamble garbage in front of it that's going to cause problems. So I double checked, yep, this is at 8,000, and that's great. Something else though, I'm telling my code that it's going to be ultimately at 8,000 once it gets put into the system. But when the system boots, it's not looking at this 32K chunk. It's looking at the last 32K chunk of this 128K. And what that means is it is actually at this address, 18000. So the first chunk starts at all zeros. The second one, I suppose if we go up, would be 1,000. Then it's 18,000. But basically you have those breaks. But what I can do in here, this is just one of these XG Pro programmers. I can tell it to select a block, and I just tell it go grab the 8,000 to the end of the Fs, which is essentially what I just got done assembling and linking. I can copy that, then I can go to the address of here, and I can paste it. And you can see I've already pasted it in the one I've got pulled up here. But now the way that this is going to work is I can write this to the chip. Again, if I go back to my webcam here, I'm using this programmer. Obviously this chip doesn't directly fit, so then you've got to have one of these little adapters that goes from PLCC to a DIP. Take your little flash chip, put that in there, put it in here, program it, pop it out of there, pop out this, put it into that socket. And I have definitely strengthened my opinion that if you're being punished for something in life, you have to work with these silly PLCC sockets and pulling things out. Not a very fun thing to be constantly pulling these out and having to put them into another socket just to pull them back out. And be careful not to damage those connectors as you do it. Now, once I've done that though, I put it in here and boot it up, and it catches that WDC. It then jumps to it, and I'm off and running, and that is working well. Now, a benefit when I get my board in, let me go pull up a picture of that. Instead of using PLCC, I'm going to put a ZIF socket. So right here on my board will be a ZIF socket, and different package, same memory. It's a SST39. Let's see if I can zoom in here for you. SF010A, but I'm going to be doing basically a DIP package, and there's going to be a ZIF socket, so I can just pop up a lever, take it out, program it, put it back in, pop the lever down. That's going to be 1,000 times better than what I'm dealing with right now. So I can't wait to get that in there. I totally get the benefit of the PLCC. Smaller package, takes up less space. And if you're not intending to pull it very often, perfectly fine. But if you're going to be doing multiple pulls in a day or in an hour as you're working on stuff, it's a pretty tough way to work. So hopefully that gives you an idea of, what does it take to get interrupts working on this board. I think, I'm doing it on, this board here, but if you were building your own board with that microcontroller, it's going to be very similar. We'll get, I'm hoping to get my boards in a few weeks from now, assuming that there aren't any challenges getting it in through customs and stuff like that. But then I'll get my board assembled and start working off of it instead of the SXB board, even though they're very, very similar at this point. But I am learning about some of these pins that I know, for example, are going to go to an LCD, and I can, instead of having the header, just have a spot for the LCD header and really dial things in for that better. And then some of this other, onboard LED, I've got some additional onboard LEDs, which will be handy. I've got the ZIF socket instead, which will be nice. And then we'll see what else I want to be messing with there, and just try to learn through. Can I get my own board up and running like this one is up and running right now? So this is a long video. Sorry about that, or if you're still listening, hopefully this was helpful. As I'm going through this is stuff I'm learning, basing it off of some of the stuff I've done in the past, but definitely learning a lot here about this SXB board and the 265 microcontroller, and then trying to get my brain back into assembly for this specific microprocessor that's in the microcontroller. It's been a while. If you caught things along the way that I'm screwing up on, let me know. If you got suggestions for improvement, let me know. If you have any tips and tricks, documentation, or samples around shadow vectors, I would love to hear it, see it, so that I can try to get a scenario running where I don't need the external flash. I can just basically move my program into RAM, jump to it, and have it run using the shadow vectors in RAM, and not having to have a ROM that they come from me. So I think my next step, next video, will probably be trying to get the PS2 keyboard to actually function, so that it recognizes the appropriate key data and then writes out those keys as I type to the LCD. So stay tuned for that, and then I'll have to think about what do I want to do after that, but I know that's probably the next step. So thanks for watching. Thanks for following, everyone.